Introduction. In this lab, we explore Faraday's law of induction, which describes how a changing magnetic field can produce an induced voltage, or electromotive force, ME, in a coil of wire. This relationship is expressed mathematically as EMF equals d phi/dt, where phi represents the magnetic flux. Essentially, any change in the magnetic environment of a coil, whether from moving the coil, changing the magnetic field strength, or altering the orientation, can induce a voltage. The negative sign in the equation shows that the induced EMF opposes the change in flux, according to Lenz's law. The purpose of this experiment is to test how changes in the magnitude of the magnetic field affect the induced voltage in a coil. Specifically, we are predicting how the EMF changes when the magnetic field increases by a certain percentage. My group predicts that the induced voltage will increase by 20% if the magnetic field strength is increased by 20%. This prediction is based on the assumption that EMF is directly proportional to the rate of change of magnetic flux. Because the coil's area and orientation remain constant, the only variable affecting the change in flux should be the strength of the magnetic field itself. Therefore, a 20% increase in field strength should cause a proportional 20% increase in induced voltage, assuming other conditions remain the same. Load test this prediction. We will measure the voltage generated as different magnets fall through the same coil under identical timing conditions. Each magnet produces a different magnetic field strength, allowing us to calculate the percent change in both the magnetic field and the corresponding induced EMF. By comparing these values, we can determine whether the relationship between magnetic field strength and induced EMF is linear, as Faraday's law predicts. This experiment not only helps confirm the quantitative relationship described by Faraday's law, but also deepens our understanding of how electromagnetic induction works in practical situations. Understanding these principles is essential for many technologies, such as electric generators, transformers, and wireless charging devices. Through this lab, we aim to strengthen our conceptual understanding of induction, test our hypothesis about proportionality, and reflect on any discrepancies that might reveal more about the physical process of electromagnetic induction.
We have a stand with a clamp to hold the coil in place, and a cushioned box underneath to catch the falling magnet safely. We choose one of 3 different coils, each with a different number of turns or diameters, to test how coil properties affect the induced voltage. We also use 3 bar magnets of different strengths to compare the magnetic field values. A voltage sensor is connected across the coil terminals and linked to the capstone software on the computer to record the voltage versus time graph. We also use a magnetic field sensor to measure the magnetic field strength of each magnet in digits mode. Additional items include connection cables, the Pasco interface, and a computer running capstone. All measurements are taken carefully to ensure that the only changing variable is the magnetic field strength, or the selected test variable. We start by setting up the stand, clamp, and cushion box. We secure one coil in the clamp so that the magnet can fall freely through the center of the coil. The cushion box is placed below to catch the magnet safely. We then connect the voltage sensor across the coil terminals and open capstone. We select a voltage versus time graph and set the sample rate to 100 Hz. On a second page, we add the magnetic field sensor to read the field strength in digits mode. We choose one magnet with the highest magnetic field as our baseline magnet. We measure its magnetic field using the magnetic field sensor and record the value. Next, we drop the magnet straight through the coil 5 times, making sure the same pole enters first each time. We record the 5 voltage spikes that appear on the graph and calculate their average EMF. We take a screenshot of the voltage versus time graph, zoomed in and labeled with values. We repeat the same procedure for the other 2 magnets, measuring their magnetic fields and recording 5 EMF peaks for each. We calculate the percent difference in the magnetic field and in the induced EMF for each magnet compared to the baseline. We then compare the ratios and discuss whether the change in MF matches the change in magnetic field strength. Next, we design a new experiment to increase the induced EMF by 20% without changing the magnetic field strength. We decide on one variable to change, such as drop height and increasing speed through to achieve the increase. We perform 5 trials with the new condition and record the average EMF again. We compare the new results to the baseline to verify that the EMF increased by about 20%. We take another screenshot of the data and note how accurately we reached the target.
Hello, my name is Said Gregorio Canton, and today I will go over the data analysis for lab number 8, which goes over Faraday's law. Lab, we had to go over how a changing magnetic field interacts with an induced voltage in a coil. We had to do this with the baseline and then 2 different shaped magnets. This is just the value of the capacitor by itself, which we plotted in the graph, giving us 3.15 just at this time. It's just a graph of voltage and time. We basically got voltage in different time intervals and arrived at this value over here for the magnetic field strength using a simple average of all of these values. The time interval was used to be as close as possible to each other to represent the delta t, and we arrived at these results for voltage. Now for the cylinder, which was the sample 1 magnet, we did the exact same thing in the graph. We used a similar time interval for each one of these results and arrived at said voltage over here. We got the average, calculated magnetic field strength, and arrived at this value right here. Finally, for our second sample rectangle, using this magnet, we did the same thing as before with the time intervals, delta t, plotted it in a graph with voltage, and arrived at different spikes for each time we created the current passing through the coil. We then computed our data and arrived at 20 MT magnetic field strength. Finally, we plotted each one of these values right here, the base shape hexagon, sample 1 cylinder, sample 2 rectangle. We arrived at the magnetic field strength as previously shown over there and calculated the difference percent, arriving at a 24.91% for sample 1 and an 82.84% for sample 2. Finally, EFM values, simply just the induced current. We calculated all of these and arrived at different percent values in difference. These are different from the previous values and they will be compared further on. For sample 1, we arrived at 31.74%, and sample 2, 17.46%. Calculate the percent errors for both sample 1 and sample 2. We simply use this formula over here, which was a division between the percent difference of the magnitude of the magnetic field and the percent difference of the EMF, which is just basically the induced voltage in the coil. Using both tables before, we divided the values of table 1 over table 2, arriving at 0.785, and then divided the values of table 1, table 2 again, 4.745. A significant percent error would have been that of 5% or more, which gives those values that are acceptable in that margin. 3. Over here, we had to work backwards. We previously were doing different voltages to arrive to our estimated 20% increase in the magnetic field if we increase 20% our induced voltage in the coil. That was our prediction. As you can see by the data before, our prediction didn't quite align with the results. However, this time we worked backwards. Instead of changing the voltage to arrive to that desired percent, we change the height with the set percentage in mind. We change the height tediously, as seen in this graph, until we arrive to the percent that we were looking for. That is 20%, which is the induced voltage in the coil as we increase the magnetic field. The data analysis. Thank you for watching.
In this lab, we tested Faraday's law by comparing the percentage change in magnetic field strength with the resulting percentage change in induced EMF. Our group predicted that increasing the magnetic field by 20% would also increase the induced voltage by 20%, and our experimental results supported this prediction. Because induced EMF is directly proportional to the rate of change of magnetic flux, the percent differences between the magnetic field values and induced voltages showed the same trend and change in the same direction, confirming that our assumption was correct. These trends were evident in our ratios: a baseline of 1, 0.78 for the cylindrical magnet, and 4.75 for the rectangular magnet. We then designed an additional trial to increase the induced voltage by 20% without changing the magnetic field itself. To reach this goal, we chose to increase the drop height, which caused the magnet to move faster through the coil and increase the rate of flux change. After adjusting the height, we were able to reach the target 20% increase and got a 0.52% error from our experimental to the calculated values. This result demonstrated that induced EMF can be increased not only by changing the magnetic field strength, but also by altering motion-related variables that affect d phi over dt. Overall, this lab clarified how changes in magnetic field magnitude and changes in motion influence induced EMF. The reflection on percent differences, ratios, and variable manipulation strengthened our understanding of Faraday's law and experimental design.
Credits: Introduction, Geomaterials and Procedure, Pedro Data Analysis, Seath Conclusion, Aaron.